In this lecture, we're going to talk about the electroscope. The electroscope measures electrical charge, both sign and magnitude. The conductor rod is insulated from the glass container. Usually we use a rubber stopper here. When the scope is neutral, the leaves hang down due to their own mass. So here is the conducting rod. It's connected at the bottom with gold leaves. It's a very thin gold film. When they're neutral, these hang down. Electroscopes can be charged by either using conduction or induction. Here is an antique electroscope from 1878. A neutral electroscope will become negatively charged when touched by a negatively charged object. A negative electrical charge will distribute across the electroscope, and the gold leaves will repel, since they have the same charge, and like charges repel. So here we have a neutrally charged electroscope. If we touch it with a rod that has a -4e charge, that charge will distribute evenly across the conducting part of the electroscope and the rod. The bar is moved away, and there is now a negative net charge on the scope. Since negative charge moved from the rod to the electroscope, the rod now has less negative charge. Remember, we're using conservation of charge. The gold leaves will repel. The leaves would also repel in this experiment if it had been done with a bar that had positive net charge. When a negatively charged rod touches the top of a neutral electroscope, the gold leaves separate. What is the charge on the leaves? Are they positive, negative, or neutral? Go ahead and select an answer now. The correct answer is A. They will be negative. What is the source of the charge that is moved to the gold leaves? Is it the charged bar, the ground, or the glass surrounding the leaves? Go ahead and choose your answer now. Hopefully you chose A, the charged bar. Charging by induction. A neutral electroscope can also be charged by induction. If a bar with a negative net charge is brought near the scope, then the electrons in the electroscope will move down to the leaves, and the leaves will repel. If the bar is removed, the leaves will go back to their original positions. This induction is temporary, and no charge is transferred from the rod to the leaves. A similar effect is caused by a bar with a positive net charge. The leaves will again repel, since like charges repel. One more piece is needed to affect a permanent charge on the electroscope. The missing piece is a ground. A neutral electroscope is connected to a ground, and a negatively charged bar is brought near. The electrons in the scope will repel out of the scope to the ground. The scope will then have a net positive charge. As with charging a sphere by induction, note that the charge on the rod does not change. Now positively charged, the leaves will repel each other. A similar effect occurs for a bar with a net positive charge, except the scope will end up with a net negative charge, since electrons will come up from the ground to the scope. Again, the charge on the rod does not change. Now negatively charged, the leaves will repel. If the charging bar is removed while the ground is still attached, the electrons will return either to the ground or to the leaves until they have a neutral charge and will fall back together. In order to leave the charge on the electroscope and keep the leaves separated, the ground must be removed before the charging bar. The electrons will now have no place to go, and a net positive or negative charge will be left on the electroscope. A positive object touches a neutral electroscope and the leaves separate. Then the negative object is brought near the electroscope but does not touch it. What happens to the leaves? A, they separate further. B, they move closer. C, they are unaffected. D, it cannot be determined without additional information. Go ahead and select your answer now. Okay, so let's see what the correct answer is. The correct answer is B. They will actually move closer together. Here we have a positive object that touches a neutral electroscope, and the leaves separate. This means that the electrons are moving to the positive object, leaving a net positive charge on the electroscope. If a negative object is brought near the electroscope, what happens is the electrons are pushed closer to the end, which causes the leaves to move closer together since they already had a net positive charge. When charging an electroscope by induction, the leaves acquire a charge from the ground and separate. How could you keep the charge on the leaves which would keep them separate from each other? Go ahead and pause the video and answer this question. Okay, so let's see what you should have written. You would remove the ground while the rod is still held close to the electroscope. When the rod is then removed, the charges will stay on the leaves as there is no place for them to go. When the leaves of the electroscope repel, there is a charge present. It could be positive or negative. The electroscope can also be used to find out the charge on the leaves. Take an object known to be positive or negative. Place it near the top of the scope and watch the reaction. So if the object's charge is positive, the electroscope's reaction, the leaves move apart. The charge on the scope is positive. If we have an object's charge is positive and the leaves move closer together, then the charge on the scope is negative. If we have a negative charged object and the leaves move apart, then we know that it's also negatively charged electroscope. If we have a negatively charged object and we move it close to the electroscope and the leaves move closer together, that means that the electroscope had a positive charge. Intuitively, it would seem that the further apart the leaves move, the greater the magnitude or size of the charge present. This is true, and the next section will talk about the force due to electric charges, which is responsible for the leaves moving against the forces of gravity and tension. So in the next video, we'll talk about electric force.